There we go. So we have been talking about circuits, and we have been talking about the four elements of every circuit, which would be the power source, the load,
Conductor.
the conductors, and the controls. Well, last time we covered the controls, and we started talking about circuits. Circuits comes from the same word as circle. And, well, might as well go through this way. Yeah, see, the resolution is way better.
Way better.
Yeah, isn't it? Sorry
Yeah.
about that. But
That's okay. It was still good.
it's still good. It's still good. Yeah, I'll use my laptop as a coaster right here. That's good luck. All right, so 121 was last week.
hmm
Oh, we were finishing controls. Okay. For current to flow, there needs to be a continuous path. So that led to a discussion of what continuity is. Continuity means that there is a path for the electrons to get from one end of the battery to the other end. And you can see here that, for instance, we have a battery, we have a fuse, we have a switch, but the switch is open. As a result, the electricity cannot travel because the resistance of the air between here and here is too high. So we can't have electron flow, which is the definition of electricity. We can't have electron flow, therefore the light will be out or the motor will be stopped. Now, this is a DC circuit, direct current. Direct current is associated with batteries, and that means it's going to be polarized. It's going to have a plus and a minus, a positive and a negative, red and a black. So typically we want to use solid lines on the positive or hot side of the circuit, and we used a dashed line to describe the negative or ground side of the circuit. Ground simply means that instead of running separate negative wires for every circuit in the system, we use the frame and the chassis of the car, which will be made of metal, instead as conductors. It's not as good a conductor as copper, but it means that we only have to put in half as many wires. And after all, the difference in resistance is not that significant as long as the grounds are working well. That's a significant issue in modern cars when just a little bit of resistance can significantly change what's going on in the circuit. And we have so many computerized circuits that are so sensitive, so low voltage, that a slight difference is going to, for instance, make us think that we have a richer mixture than we really do, or that we have more air coming in than we really do. Okay, so we can see that this is a switch, and this switch is called open, which is to say the switch is off. As you can see, there's no continuous path from here to here like there is from, oh, I don't know, here to there. See, electrons can flow here because there's a continuous path without interruptions, without significant resistance. Low resistance path, I should say, just like the conductor in a wire. See, we got a low resistance path here, and the insulation around the wire is a high resistance path. That makes it so the electrons want to flow down this path, but they don't want to leave. There we go. I was just going to ask you where Anna Maria is, and she appears. There we go. Okay. So, go like this. And I used for you well, for instance, I said, look, voltage can jump and high voltages can jump further. So what we do is we try to separate, for instance, on a wall, we separate these two because there's 120 volts between them. We have to keep them far apart. The lower the voltage, the less distance apart they have to be. But for instance, if you have over 6,000 volts, I think, you have to have like 12 feet of distance between any hot conductor and a chain link fence. Why? Because the chain link fence is grounded. Now, in alternating current systems, ground means a kind of different thing, but it also kind of doesn't. It's electrically important, let's say, electrically significant. It's tied to one of the conductors, the ground dead conductor. Okay, so here's what we do. The switch looks like this. When it's open, the resistance is very high. That's why, in fact, it's so high that on our meters, it would read infinite. As a result, voltage stays the same, resistance goes infinitely high, we get no current flow. When, however, the switch is closed, now it basically has the same resistance as just an equivalent length of wire. Low resistance makes it possible for current to travel, electrons to travel, and that's what's going to power our load. All right, so I use the analogy of trying to get to a castle up on a hill, and the problem is the drawbridge is up. Well, if the drawbridge is up, that means that you can't just walk across. There's no path. So this dude's over here and he doesn't know how to get across. He can't get here because the drawbridge is up. The resistance is too high. The resistance to traveling is too high. All right. Well, the third type of control besides switches and resistors is variable resistors. And this right here is the symbol for a resistor. Switches and fuses, I'm sorry. This right here is a variable resistor. That means that it's not just a resistor, but we can change the resistance from very little to a lot, maybe even enough to stop all current flow at all. And this is typically met with like volume knobs or maybe a fan control or something like that. Because sometimes we don't just want on and off. We want, you know, half on, half off, or 3/4 on, or something like that. So that way we don't just have a radio that's either going full blast or it's off. Okay, so we started talking about speed control on motors. And that led to a discussion here of direct current and how as soon as you turn it on, there's a whole bunch of power. So the good thing is that I brought a friend. Now, Chuck, you got a oscilloscope? Little Bantaje. There you go. Now, this was Snap-on's state-of-the-art oscilloscope 20 years ago, which is why it's cheap now, because that's like 4 generations ago. So I want to go to Waveform Viewer, and this is just like the cheap scan tools that you get from Harbor Freight and places like that. If it's giving you what you want or offering you what you want, you say yes. If you want to do something different, you press no. So it says Waveform Viewer. You know, I've been having problems with glare. For some reason, this camera is insanely sensitive, really sensitive to glare. Come on now. No, I don't know if that's better or worse. Okay, Waveform Viewer. So that's what I want. So I'm going to hit yes. It asks me for AC pulse generators. Yeah, I know it's got this big splotch right here. That's a birthmark. That was a joke. Low frequency, less than 120 hertz. So that's what I want. And we can see that it says 14 volts up here, positive, negative 14 volts here, and we've got 0 volts there. Okay. So here's what I'm going to do. This right here is a 12-volt battery, nominal. And when I go like this, what you're going to notice is that it goes up to 12 volts and it stays there. Yeah. Now, I suppose I could come back here like this. No, because it's not giving me what I want. I could come back.
Yeah, right there's good.
Yeah, right. So I can stick something under it. That would be optimal. Stick something like that.
There you go. Yeah.
That's probably too far. double A instead of the D. There you go. Okay, so let's say, yes, that's what I want. How about I come in here and change the bottom to, oh, I don't know, -1.1. There you go. That's going to give me a bigger waveform. Okay. So then I come in like this, and you're going to see that that line is going to go up to 12 volts and stay there. That's direct current. And that means, in case anybody's remembering last week's lecture, all of this stuff is filled up with energy being delivered. That's why direct current motors are way more powerful than alternating current motors. Now, we talked last time about three-phase and how we're trying to simulate direct current without delivering it. Have you guys seen that movie, The Current Wars? I've probably seen it 4 times now. It's on cable. And what really was holding back alternating current and what was keeping Edison in business was the fact that he was the only one that had a motor that would work. And it wasn't until Tesla came along that someone figured out how to make a motor with alternating current. And after that, it was no contest. Nobody wanted to DC anywhere because it just doesn't travel well. It doesn't travel well. The further away you get from the power plant, the less voltage you get. So it's like the house right next to the power plant would be really bright, and then you go down the line and it just kept getting darker and darker. Now, so one thing I wanted to point out, because we're going to be talking about it today, is -5. I'll come up here to +5. Remember, oscilloscope displays voltage over time. Voltage on this scale, time on this scale. This goes +5 volts, -5 volts. This says 50 milliseconds, which is 1/20th of a second. And as you can see, it's already given us the sine wave. Well, the leads aren't connected to anything. So where's the sine wave coming from? This is induced voltage, which means it's created by magnetic fields. Now, what I noticed today was I take these leads and I put them in my hand. If I spread them this way, they do one thing, but if I spread them this way, they go away.
It's weird.
Because what I'm doing is I'm basically creating an antenna. So what I can do here is I can bring this down to, well, let's say 1 or 2. Yeah, I might make the wavelength easier to study. So anyway, Chuck, these oscilloscopes probably cost you $200 with the software. And what they'll do is they have the pin out of the connectors, and they also have testing tips and stuff like that. I mean, so you get software version 6.0 goes up to 2002. Well, who cares? For $200, this gets you down the road with professional test equipment. Now you can see that when I hold it like that, making the waveform bigger. When I go like this, it makes it smaller. I think it has to do with going parallel to the magnetic field and going perpendicular to the magnetic field. This is all induced voltage, but you can see it's almost, 1 volt, 1.5 volts.
I'm sorry, what is this exactly measuring? Exactly?
That's my question. What is it measuring? It's measuring voltage created by magnetic fields. Okay, where's the magnetic field coming from? Is it coming from the computer? I suspect it's coming from the power supply in the computer.
Probably.
Current creates magnetic fields. So wherever the current's coming from, that's what it's doing. Well, I don't know. I would have to start turning off loads and see what makes this go away. But yeah, the cool thing about this is it shows you what's really going on. Oh, speaking of which, Chuck, do you have anything that can detect bugs on cars?
Hello. No, I do not.
Can you print your own PCB, printed circuit boards?
What was that again?
Can you print your own circuit board?
No. All I could do is remove the surface mount IC chips off the motherboard.
Okay. All right. So that's the sine wave. And I wanted to show you that because I thought it was kind of useful and exciting. And that's what we were talking about when we were talking last night. Incidentally, Gabe, I have a 3-phase motor controller here that I was hoping maybe I'll get to demonstrate. All it is a relay. All right, so here we go. I want to test the voltage in coming out of the wall. So I'm going to come over here to 200. And I'm going to come down here to negative 200. Can you see how I'm highlighting different aspects?
Yeah.
Yeah, so I'm going to come down here to negative 200. Now, if I wanted to, see where it says view, if I hit yes on that, it asks me, do I want to do channel 1, channel 2, or both at the same time? That's really kind of groovy. Okay, so what happens is if I put my little leads here and here, there gets a sine wave. Now you say, well, that's not 120 volts, that's like 177. Well, yeah, if you multiply 120 times the square root of 2, which is how you find peak voltage, it's about 177 volts. But the important thing is, I just wanted you to see what alternating current looks like. This is what's coming out of the wall. And we can see that, remember, this is 50 milliseconds, that's 1/20th of a second. We can see that we get 3 wavelengths in every 1/20th of a second. So multiply 3 times 20, what do you get? You get 60. That's 60 cycles per second, 60 hertz. So when we describe this electricity, we would call that 120 volts AC, single phase, 60 hertz. Now in Europe, it's 50 hertz, it's different. Or it could be 240 volts, or I mean, it'd be whatever voltage, but I'm just saying 120 volts, alternating current, single phase, 60 hertz. That's why I pointed out when I was showing you that, well, someone's got their mic on. Yeah, it's causing feedback. That's why I was pointing out when we were watching that slow motion video on that solenoid video last time, you could see the lights flicker.
Mhm.
Well, look, right here, you've got minus 177 volts. But as it comes positive, it crosses 0. Well, with 0 volts, you got 0 current. That means the light goes out. Then it goes back up, comes back down. When it goes to 0 volts, you got 0 current. Light goes out. So 120 times a second, the light goes out. Why don't we see it? Because the fastest the eye can discern is about 25 times a second. So it's going on and off. It's going out and, it's going on and off, and we just can't tell because it's happening so fast.
Wow.
Yeah. So that right there is the sine wave. Okay. So let me see what else we got. All right. And as you can see, there's a whole bunch of empty space in a single phase power that is just wasted space that keeps us from making our motors more powerful. DC, you can see the whole block is filled up. As a result, it's capable of producing a great amount of power. Single phase AC, it's got issues with that. That's why we came up with 3-phase. It's an AC way of mimicking this. And we'll see that when we start talking about alternators. All right, so let's make sure we understand meter usage. I'm going to come in here like this with my beautiful Fluke 117. If I was you, I would get a meter. I would get one of those Chinese meters because you're probably going to blow up your first one anyway. And it's got all the features this has. Probably last as long too. All right, so that's a D battery. That is a AA, and that is a AAA. Okay, so what's the difference between them? They're all 1.5 volt batteries, so they should all have the same voltage. The difference is, a small gas tank, a big gas tank, and a medium gas tank. The question is not the difference in pressure. The question is, how far will it get you? So if you got a boom box, you want to have the big D battery. If you got a TV remote, you want to have the AAA. Now, as I said, it's nominal 1.5 volts. That means it's got to be around 1.5 volts, just like our 12 volt battery isn't just 12.00 volts, it's 12.6. or depending on the state of charge, it could be anywhere less than that. So we put our meter on the capital V that's got the solid line with a dotted line underneath. And just stick it like that, and we get 1.375. This is the battery I just took out of the oscilloscope because it's dead. Turns out this battery is 9 years old. It lasts 9 years because I didn't use it that much. But this is supposed to be 1.5 volts. It's 1.375. It's significantly discharged. Problem is, after you get down past a certain voltage, the devices won't work anymore. Let's look at this one. That one is 1.476. That's about a half volt less than 5 volts. I took this out of a clock, I believe, because a clock is a motor circuit and it was not very happy about having low voltage. This is a new battery that I pulled out of my refrigerator recently, 1.528. Actually, I didn't know. I pulled this out in like September. So it was sitting on this table during all those hot days. And I think that's why it started self-discharging. If we looked at what the voltage was, you know, a month ago, it was probably higher. And let me see right here. That's a 9-volt battery. And let me test that. Remember, keep your fingers behind the little guards. And it says 9.48. So that's still in unused condition. Okay. Now, what about the big boy? All right. Well, here's what I'm going to do. I'm going to deliberately put the leads on wrong just to show you what happens. See, it's going to give you the right voltage. It's just going to have a negative sign in front of it that tells you you've hooked up your leads wrong. 12.75. It's been sitting out here for a long time, but I haven't been really using it for anything. Now that I got the power probe in here, I will. 12.75. So remember, direct current is associated with batteries. So if we're dealing with a circuit that's associated with batteries, chances are good we're going to use direct current volts to test it. I don't worry about teaching students how to do volt testing because it's very safe as long as you got a decent meter. It's very safe, and as long as you know what you're doing. It's very safe, and you can't really hurt anything, and it tells us a bunch of useful stuff. Well, right here is what's coming out of the wall. We need to understand that there's direct current associated with batteries, and then there's alternating current, which is created by rotating magnets. Okay, well, this stuff's created by rotating magnets, whether it's at Hoover Dam or a wind turbine or anything like that. It's created by rotating magnets. So now I'm going to turn my volts to AC. You can see right here, it's got the sine wave, the squiggly line, whichever you want to call it. And if I come in here like this, we can see that it says 118.2. Now, about an hour ago, this was 119.4. What happened? People came home and they started using their electrical appliances, their stoves, their microwaves, whatever, TVs. And what happens is, just like when a bunch of people use water while you're trying to take a shower, the water pressure goes down. Well, when a lot of people use electrical loads, the electrical pressure goes down, and electrical pressure is called voltage. You can see it's 118.2, 118.1. It's changing. It says volts AC. And there are enough AC things going on in a vehicle that we need to be aware of how to test it, how to deal with it. That's my theory on that. Let me see where we're at. All right. Boy, we made all kinds of progress. Yeah, I'm reviewing too hard. Okay, we're talking about electromagnetism. There's a relationship between electricity and magnetism. Passing current through a conductor creates a magnetic field, and that's going to be proportional to the number of coil windings and how much current we're pushing through it. Those are windings, those are turns. Incidentally, Electro Boom has some good videos.
Bless you.
Excuse me. But Engineering Mindset has some good videos, but the problem with Engineering Mindset is a bunch of that stuff, it gets to be really, really hardcore, and then it's like, okay, what the hell? I thought I understood it, but now I don't. It's because some of their stuff is really clear and basic, and some of their stuff is really freaking hardcore to where it's like, you don't need to know that. Not for this class. That's more like electrical engineering stuff. All right, magnetic lines of force created by magnets. We know about that. And we know it's polarized. We talked about coils. We talked about solenoids. We talked about relays. Incidentally, that right there is a relay. Yes, I did. And this is like a three-hander presentation. So I'm going to put my beautiful, beautiful power probe. There we go. So I got the battery hooked up to 12 volts. The beautiful power probe longs to serve us. And sure enough, you can see with your beautiful resolution, you can see it's got 12.7 volts. Helps to have a better resolution camera, huh? Should have got that a long time ago. So anyways, my point was, this is the relay. What is a relay? A relay is an electromagnetic switch. It's an electromagnetic device that uses a smaller current to control a larger one. Well, the large current being controlled is going from here to here. That's why the bolts, that's why the screws are so big. There you go. Now, the small current is this little rascal right here. And one side of the coil is connected here, and the other side of the coil is connected to this ground where it would be bolted to the vehicle. So I'm going to connect my auxiliary ground to that. And I'm going to come in here. That tells me the coil is good, incidentally, that it has a continuous path. Now, if I push forward on this, sorry, if I push forward on this, it's going to put 12.7 volts right here. If I pull back on it, it's going to ground this. So I'm going to push forward on it. And when I do that, I'll have 12 volts from this little nub to this ground. And listen. Hear that? Listen. Oh, sorry. Hear that? That's a relay closing and opening the switch. Now, just because the switch works doesn't mean, just because the switch moves doesn't mean that it actually provides a continuous path. For that, we will need to put this on continuity. I believe we talked about that in this class last time, right? Right?
Yeah.
Continuity tester goes like this. Hear that? Okay, so what I'm going to do is I'm going to put this here, put that there. Ah. Yeah, this is the good old three-hander demonstration. Yeah, it's like using chopsticks.
Mr. Roadcliffe,
What?
before you do that, is that setting too low for that 12 volts?
No.
We're talking about on the scale when you have the sound on the ohm meter that it's
Right. I'm not testing the coil.
Okay.
What I'm going to do is thank you. I'm going to activate this coil and I'm going to check to make sure that there's a continuous path between on the power side. Yeah, you're exactly right. In fact, well, you could test that right now. See how many ohms it is. Oh, it turns out it's only 6 ohms of resistance. You know why? It's because this is a big old relay and it draws a lot of current. So yeah, Chuck's brought up an important point. Don't get fooled by the continuity tester. Just because it doesn't beep, all that means is that it's got more than 52 ohms of resistance. Could be open or it could be not. This only has 6 ohms, so it beeps, and you'll notice it also shows up on the display. But what I'm doing here is I'm checking to see if I activate this coil, is there going to be continuity between these two lugs? Because one of these lugs bolts to the battery cable, the other lug bolts to the starter cable.
Yeah.
So this is exactly what I've drawn. Let's see. Now, if this works, when I activate this coil, the switch is going to close and we're going to hear the continuity tester. Listen. See that? See the meter reading change? And you can hear the continuity tester at the same time. So this relay is good. Now, am I sure that it can pass 200 amps without significant resistance? No, but I see that it can pass milliamps without resistance. I can see it's not grossly bad. So it's hints. Why do we want hints? Because this stuff gets really, really expensive and there's no return on electrical items. So we need to understand electrical, right? I'm going to demonstrate this stuff for you so you can always go back and look at it. We need to understand electrical enough to where we can make some decisions about whether something's bad or not, or whether we need to investigate further or something like that. Now there's a relay. Got relays all over the car. Why do we need relays? We need relays because we want to control high current loads without having to switch that high current, say, inside our computers. So what we do with our computers is we send out a relatively low, small current, and that creates a magnetic field that's going to close that switch or open that switch, depending on how we have it wired. And it can control, 250 amps with, milliamps. So that's what the relay is all about. Now, just to show you, that thing right there. That thing right there is a three-phase motor controller. It's a relay. See, it's like this is where the 3 huts get connected. And then this is how heavy duty this thing is. This is like a 50 amp 3-phase motor controller. And this is where you hook up to the motor, line 1, line 2, line 3. Fortunately, it's got a 120 volt coil, which means I can activate it with house crank. Let me show you what that looks like. See, what I'm trying to do here is I'm trying to show you, I don't care if the relay is big or if the relay is small. Look. See that? And what it's doing is it's connecting the voltage source to the motor. Watch. I'll show you from the side. See, it's got this lug, these 2 lugs are connected. This is the one that's got the line. This is the one that's got the load. When I go like this, it connects them. So it don't matter whether we're talking about industrial motor controls or whether we're talking about your windshield wiper relay. It's all the same stuff. Now, the good thing about this, though, is come in here with a screwdriver. We're going to make sure that's unplugged, right, Chuck? If I come in here with a screwdriver, come in the other side with a screwdriver, there we go. There's the coil. It's encapsulated in plastic, but there's the coil. This thing right here, in case you were wondering, is the laminated iron core. And if you've been watching your engineering mindset videos, it's got a laminated iron core, which is just a whole bunch of steel plates that they put a whole bunch of plates instead of one plate. So it protects you from eddy currents, what's called eddy currents. Now, what's the point of the iron core? It's going to make this coil much more efficient and much more powerful. So that's the coil. Now, Chuck says, I don't know, is that coil any good? Well, first of all, since current flowed enough to create a magnetic field, we know that the coil's good, but just to keep Chuck happy, so he doesn't complain to the superintendent of schools, I'm going to come in here with my meter set on continuity. I'm going to do myself a favor and check to make sure the leads are good before I go to testing. I come here and here on both sides of the coil. And what do I see? I have 30 ohms of resistance. 30 ohms of resistance means at 120 volts, I don't know, was that 4 amps? Of course, that's going to change when it gets hot. But either way, I've got continuity. That means the coil is good. If the coil is good, then when I pass voltage into it, there's going to get current flow. And if there's current flow, it's going to create a magnetic field. If it creates a magnetic field, then these contacts are going to close. Now, these contacts are replaceable because, as you can imagine, there's all kinds of electricity hitting those. I mean, it's just like the breaker points on the old distributors, right, Chuck? It's just way bigger ones. Those are almost the size of dimes. So I know the coil's good. Now, why am I showing you this? Because this is one of the big things that people don't know how to do, and it's going to negatively impact your ability to be successful in this genre. So I'm going to put the iron core back in the coil, shove the coil back in. You know, these are like $600 or $700. You want to make sure these are bad before you tell your boss they're bad. Because if he orders one, he or she orders one, and it turns out not to be bad, that could be the last day you work there.
Mr. Roadcliffe, can I ask a question?
Yeah, you just did.
Another one.
Yeah, of course.
Your oscilloscope, if you put that oscilloscope on that and you hit that switch, will we see a graph?
If I put it on the coil?
Yeah, when you turn the switch.
Yeah, actually you would. That's an interesting question. But of course, with my jacked up hands, the question is whether I'm going to be able to get this stick the coil back in. Let me fight it for a minute.
But I wouldn't want you to hurt yourself.
It's not a matter of that. It's just makes me sick how freaking crippled I am now. It hurts my feelings, Chuck. I mean, this is stuff you could get done in a freaking millisecond. So, anyways, that might work better.
I feel bad. It takes me 45 minutes to get to the bathroom in the morning. I can't even sit up when I first wake up.
Really?
Yeah. 2 of my spines are degenerating.
That sounds like fun.
It's not. It's very painful.
Yeah, I bet. Well, I thought it was because you had the mouse on top of you.
No, I did though. I sleep with my head in a hamper. It's pretty sad.
What?
I have like a pop-up hamper that I sleep in so they don't crawl in my face.
They? You call us friends?
Well, no, there's more than one, believe me. I've had them for a year now, so do the math on that. They can breed every 50 days.
You know, actually, Chuck, you know what helps when you're trying to do this job? Is don't try to put it in upside down. Turns out that complicates things significantly. And then after you've done that, come on, little doggy. Huh. That sounds like a good sound. Sounds like good luck. There we go. All right, so let's try this again. Take this here, right there. Okay, so what you're asking is, if we were to hook up the oscilloscope to this, would we see a voltage spike? Yeah, we would, and it would be alternating current too.
But I wouldn't want you to do it and get yourself shocked. So it was just a question.
Oh, okay, all right. All right, appreciate that. Okay, so all I'm saying is what we're trying to do here is I'm not trying to show you how to fix a Nissan. or I'm not trying to show you how to fix the Toyota. I'm showing you how to fix anything that has a relay to it, whether they call it a contactor or a relay or a motor controller or 17 million other names for what's exactly the same thing. We're trying to think of things in terms of basic fundamental concepts as opposed to, part number 4265 on a Nissan. Incidentally, someone asked me, I better should not say that. Yeah, someone just told me that they bought a Rogue, a 2014 Rogue. I'm like, people never ask me what kind of car you should buy. Well, that's the CVT, man. Okay, so here's the continuity. Here is the open, most common failure in a coil. As a result, we're going to not have current flow, therefore no magnetic field. Talked about the resistance of a conductor. We talked about testing for resistance. We talked about diodes, actually, and then we talked about transistors. Okay, good. Well, did we talk about solenoid valves? Which is just a valve connected to a solenoid.
Briefly, I think.
Yeah, I don't think we have to talk about that too much, but let us talk about something we should talk about. And let me know how this is working out for you. Turn this other way, like that. Okay, so I'm going to pass some current through this coil right here. And I'm going to put an iron core like I just showed you for increased intensity.
No.
Who, me?
No, my cat was climbing on the keyboard. Kicked me off last week, remember?
Yeah.
That is proper.
Well, that'll be a snack after the dogs take care of the baby problem you got. Okay, so I've got coil here and I got coil there. You'll notice that this coil has way more turns than that coil.
Yeah.
Okay. Well, this is what's called a transformer. And a transformer, we didn't talk about this, right?
Mm-mm.
Okay. A transformer is used to changes the voltage we have into the voltage we want. So they told us on a staff meeting on Monday that we could have free vaccines, which they wouldn't do if they weren't planning on getting us back into school. And, Newsom opened up the state allegedly. So we'll see how that goes. But there's, keep the lamp of hope lit that we'll get back in the schools. Then I realized what I should do, since the red Corvette's been apart for 10 months, is what I should do is just throw a freaking pizza party and get my top wrenches from last year to come in and put the Corvette back together. Probably take them like 3 hours, as opposed to having a whole bunch of newbies who have never touched a Corvette doing this job. Oh, and then Chuck, you'll be glad to know that I was driving the Z06 last night and I was like, man, that's a weird bearing noise. And it sounded like a bearing noise. And it's like, okay. So, I'm putting the clutch in and out, but the transmission's in the back. So I'm like, well, so it couldn't be a differential and it couldn't be the transmission or the front bearing of the trans. Now I realize it's got that freaking torque tube in it, which has a bearing in the front and the bearing in the back, and the bearing in the front is right next to the clutch. I was like, damn it. If I've lost that front torque tube bearing, that's like $5,000 to change that.
Mm-mm.
Or I could take it to Chuck Reyna Automotive, get it done for $3,250.
You can't get a used one from Pick Apart?
Oh, no, come on. I mean, no, it's like $5,000 worth of labor. And while you're there, you might as well do the clutch, right? Because you got to pull the rear end out, you got to pull the trans out, you got to pull out the torque tube, you got to disconnect the brakes. Oh man! So I was like, yeah, I hope that ain't what it is. Just turn up the radio, right? So it changes the voltage we have into the voltage we want. Why is that important? Well, because, for instance, I have the battery charger for my laptop that puts out 20 volts, but we start out with 120 volts at the wall socket. or the charger for my scan tool, which starts out at 120 volts and then kicks down to 12, or the charger for your cell phone, which goes from 120 volts to 5, we often need to change the voltage. Now, fluorescent lights, we go from, say, 120 volts to, say, 40,000, so that it'll strike an arc all the way across the bulb, a 4-foot bulb. Or the ignition coil, we go from 12 volts and then we kick it up to 12,000, 36,000 volts, so that the arc will jump the spark plug gap, because it takes high pressures to jump far long distances, and it takes high voltages to jump air gaps. You know, places where you would think the resistance was very high, because it is. All right, so this right here we call the primary, because that's where the energy is first. What in the world? This right here we call the secondary, because that's where the energy is going to be last. Okay. So how does it work? That's better. A little bit. There we go. That's better. Okay, so how does it work? Well, there's a second part of electromagnetism that we haven't talked about that we need to talk about. And that is passing a magnetic field. We didn't talk about this, right?
I don't think so.
Yeah, I don't think so either. Tell you the truth, I'm confused though. Passing a magnetic field across a conductor creates voltage or current. And folks, I got to tell you, that's all there is to electromagnetism. We're either creating a magnetic field or we're creating current and voltage. That's all there is. So we're actually on the downhill when it comes to electromagnetic devices, which is amazing because, you know, electromagnetics is a big deal. Okay, so passing a magnetic field across a conductor creates voltage or current. Basically, remember the lines of force, the flux lines that go around a magnet? Well, when you break those with a conductor, those magnetic fields start to interact with the electrons inside the wire, because the electrons are charged particles. So depending on which polarity they have, they're either going to push the electrons in one direction or they're going to pull the electrons in the other direction. Because electrons are charged particles, therefore they can be manipulated with other charged particles or magnetic fields. So the question is, how much voltage and current? Well, the first two determinants we already know. We know one is proximity, how close all the parts are together. And two is the number
Windings.
of coil windings. Good. Good, good, good. Well, number three. Number three is how strong is a magnet? Remember, one of the things that determines how strong a magnetic field is that gets created by the flow of current is how much current. Well, one of the things that determines how much current gets created is how strong the magnet is. So it's just exactly the opposite. First two are the same. The third one's exactly the opposite. Now, there's a fourth one. The fourth one is the speed. I think this is how I want to do it. I didn't used to do it this way. I used to say the speed of the cutting action, and that referred to cutting the magnetic lines of flux, but I think it confused people. So I'm going to say speed of relative motion, and you tell me which one is easier to understand. When I say relative motion, I'm saying you can move the magnet across the conductor, or you can move the conductor across the magnet, or you can move both That's what relative motion means. That means compared to each other, they're moving. Now, the speed. That's why if you look at an alternator is running at 12,000, 15,000 RPM all the time. That's also why, in case you're wondering about the old school, back in the day, we used to say if you want to charge the battery when you're jump starting, what you want to do is you hook up the battery cables and then you bring up the engine speed to like 2,000 RPM. That's because the faster the charging system goes, the more efficient it becomes. So, speed of the relative motion just means either the magnet's moving fast across the conductor or the conductor is moving fast across the magnetic field, or both. And that's what determines how much current or voltage gets created when you pass the magnetic field across a conductor or vice versa. Let me show you a short part of a video. You can watch the whole video at your leisure, but there's only a small part of it that matters to me. So let me get that to you. It is an engineering mindset video. So let me stay out of your way here. As I say, there's a bunch to this video, but I didn't find it useful for our purposes. And of course, well, I had, okay, so I'll just find it again. There's also an Electroboom video about how to make a taser. Oh, this magic of magnetism video is pretty good. It too gets complicated. Well, that's very interesting. Why is it, Chuck, that I was just talking about taking out a rear end and here's a video on just that?
Yeah.
Muy sospechoso.
Happens to me all the time too. It's weird.
It's a good thing I only think about decent things.
Oh yeah, of course.
Yeah, right. Like, what the hell? Alternator. So what you want to watch is you want to watch the alternator video. But what I'm going to do is I'm not going to watch the whole thing. I'm going to start. I'm going to start about 7.5.
Designs, but this is an example of a simple 3-wire design with the speed of the vehicle. The faster the vehicle travels,
it gets kind of complicated. Now I'm going to come back here to about 7 minutes. Right there. I'm going to hit this like this. We'll watch about 6 minutes of this.
Is able to power the electromagnet.
See, it's ready to get as complicated as you want, but this is way too complicated for you guys right now.
By itself via a diode trio.
Ready?
Which converts the 3-phase AC into DC.
Begin.
The voltage and current produced by the alternator will vary with the speed of the vehicle. The faster the vehicle travels, the faster the crankshaft rotates. And so, the faster the alternator also rotates. This increases the voltage and current. To control this, another component is used called the regulator, which is mounted at the rear of the unit. This is an integrated circuit board which monitors the output of the alternator and varies the current flowing through.
Okay, I've shown you that animation for like 10 seconds now, so let's take a 100-question quiz on. Kidding.
Electricity is the flow of electrons in a wire. The copper wire is made from millions and millions of copper atoms. Each atom has a free electron. This is an electron which is able to move freely between other atoms. It does move 2 other atoms by itself, but this occurs randomly in any and all directions, which is of no use to us. We need lots of electrons to flow in the same direction, and we do that by applying a voltage difference across the 2 ends of a wire.
Right, we create a pressure so we start to get flow in the direction we desire.
Forces the electrons to flow. If we reverse the battery, the electrons flow in the opposite direction. When electricity passes through a wire, an electromagnetic field is generated around the wire. If we place some compasses around the wire and pass a current through it, the compasses will align with the magnetic field. If we reverse the direction of current, the The magnetic field reverses and the compasses change direction.
It's got polarity, right?
If the wire is wrapped into a coil, the magnetic field becomes stronger. Each cross-section of wire still produces an electromagnetic field, but they combine together to form a larger, stronger magnetic field. The electromagnet produces a north and south pole, just like a permanent magnet. If we increase the current to the coil, the electromagnetic field increases. We can also do the opposite. If we pass a magnet through a coil of wire, a current is generated in the coil.
Now, see, this right here is an ammeter. And you'll notice that when you pass the magnet this way, the ammeter goes that way. When he retracts it, it's going to go the other way. Watch.
The dial on the ammeter indicates a current flowing in the forward direction. This is therefore generating a DC or direct current.
Why? Because the magnetic field is pushing the electrons because they're charged particles. Now, when you go the opposite direction, it's going to pull the electrons the other direction because they're charged particles. Opposites attract, like charges repel.
When the magnet stops moving, the dial returns to zero. When the magnet is moved in the opposite direction, the current flows in the opposite way, and the dial indicates a reverse current. If we move the magnet in and out repeatedly, the current will therefore alternate between flowing forwards and backwards. This is how AC, or alternating current, is generated. The current is continuously alternating in direction. If we move the magnet faster, a stronger current is generated.
Number 4.
If we use a stronger magnet, then the current also increases.
Number 3.
If we use a larger coil with more turns, then this will also generate a larger current.
Number 2.
Instead of using a permanent magnet, we could use an electromagnet. As we move this in and out, it will also generate an AC current in the coil.
That's how an alternator works. The regulator regulates the amount of current going through this electromagnet, and that's going to determine the alternator's output. Yeah, it's not that bad. One of the problems we have, electricity freaks people out because it's invisible. I mean, who knows? It's like talking about, internal parasites. You can't see them. But once you stop freaking out, you're like, oh, okay, that makes sense. I mean, if I vary the current going through this coil, it's going to vary the strength of the magnet. If the magnet's not that strong, I'm not going to get that much output out of these big coils. Well, these big coils is the alternator output. So if I want more alternator output, I put more current here. If I want less output, I put less current here. Okay, the regulator's job is to say, okay, how much battery voltage do I have? Do I need to give it a lot of juice or a little bit of juice? Actually, on a modern car, the PCM's like, okay, well, can I shut off the alternator now, save some gas? Now, this is one way to do it, but it's not the way it's really done. This is how it's really done.
But with the electromagnet, we can adjust the current and voltage to vary the strength of the magnetic field.
A voltage regulator
This
works.
lets us control how much current is generated in the coil. Instead of moving a magnet in and out of a coil, we can generate a current much easier by rotating the magnet and placing the coils around this.
What did I tell you? Alternating current is created by rotating magnets. Now, you can put a big old windmill and attach it on a shaft to this magnet and spin it that way. You could put a big old propeller and put it in Hoover Dam horizontally and let the water spin it. However you want to do it, if you spin this thing, it's going to create alternating current, and that's how Tesla and Westinghouse won the world.
The strongest part of the magnetic field is at the ends where the magnetic field lines converge. You can see the magnetic field lines by sprinkling iron filings over the magnet. With the magnet between the two coils, there is no current generated. But as the magnet starts to rotate, the strongest part of the magnetic field gets closer and closer to the coil. The coil experiences a changing intensity of the magnetic field. This will cause more and more electrons to be pushed forwards up until its maximum intensity.
As voltage goes up,
Then the magnet starts to move away from the coil.
voltage goes
So the
down.
magnetic field begins to decrease, and so does the current of electrons until it reaches zero again. And now the opposite end of the magnet begins to get closer to the coil. and this pulls electrons in the opposite direction. This again reaches a maximum point and then decreases back to zero. And so, if we were to plot this current on a chart, we would get a sine wave with a current flowing in the positive and then the negative regions.
You saw that.
This setup gives us a single phase AC supply. But we have all this empty space between the coils, which seems a bit of a waste.
Now what he's going to do is he's going to start introducing three-phase. Gabe, if I was you, I would watch the next freaking 5 minutes of this video because it's going to explain three-phase in the easiest possible way. Now, engineering mindset, it's kind of hardcore for this class. I only use pieces of it because it gets really, really hardcore in terms of alternators. I mean, maybe Chuck could understand it, but for our practical, look, with us, if the alternator doesn't work, we replace it. We're not here to do a big old freaking autopsy on it, right? Right? If my dog's out in the backyard dead, I'm not going to do a freaking autopsy on it. I'm just going to take it to VCA, right? Or throw it over Chuck's back fence. That was nice, teacher of the year. That was. I told you I used to be a terrible person. Anyways, and I haven't gotten much better. So engineering mindset has a bunch of great videos, and that's one of them. So also the video I want you to watch for homework is this beautiful video about how to make a taser. Why? Because how do you make a taser? You make it with a transformer. For instance, this guy's kind of crazy, but a lot of times he's much easier to understand than engineering mindset because he doesn't take himself as seriously. Right here.
To take the high voltage from a low voltage source, you need a transformer. A transformer is of the inductor family, and its output to input voltage ratio is proportional to the secondary to primary winding number of turns. Also, it only works with AC signal. So if the secondary to primary turn ratio is 100, if I apply 10 volt AC at the input, I'll have 1000 volt AC at the output. Now for my transformer, I use this one that's generally used in a car.
Remember them days, Chuck? The old ignition coil for all 8 cylinders? Yeah, it's an ignition coil. What does it do? It takes the 12 volts coming in from the battery and it kicks it up to 12,000 volts or 24 or 36,000 volts, whatever voltage we need to get to create an arc. Whatever voltage we need, that was Rudy. Whatever voltage we need to create an arc to jump across the spark plug. Like, for instance, there we go. So, hey! Look, if I hold my garden hose at my curb, it won't go across the street. But if I get a pressure nozzle, now the pressure will be high enough to go across the street. But hey! How are you, dude? Good to see you, man.
What's up?
Hey.
So are you homeowner or what?
Not yet.
Okay. All right.
Hopefully by February 1st.
That's 3 days.
Yep, hopefully.
Oh, cool. When's the party?
After I become a homeowner and I move in.
Okay, 4 days.
And I get situated.
Okay, so the point I was trying to make was,
So maybe next month.
for instance, what does the fire truck do? They used to call them pumper trucks. What does a pumper truck do? Well, it's got the same water pressure we have at our house, like 80 PSI. But what it does is it puts it into a pump. So now we can kick it up to 300, 400, 500 PSI. That's why you don't let go of that nozzle on the front of the fire hose because it'll whip around and kill somebody. That's why they got to have 3 guys holding it like this because it's got so much pressure coming out. Why? So you don't have to stand within 4 feet of the fire, right? So you can stand on the ground and shoot it into the 2nd story window. Get it? So we increase the pressure so it will go further. And that's what the ignition coil does. All right, watch. Come on.
It's called the car ignition coil and is responsible to generate sparks across the spark plugs that ignite the fuel in the cylinder. This specific transformer has this wire arrangement and it has a secondary to primary ratio of around 60.
False, boomer. I mean, false, millennial. It's way more than 60 because that would mean that this output was like 700 volts. It's not. It's like 14,000 volts. So he's way off on his numbers, and the next thing he says is going to be wrong too. But he means well. So let me show you. He creates a circuit.
And capacitor start.
And I wanted to show you the circuit. Look, that's a battery, we know. This is a switch. That's a capacitor. I'm probably not going to teach you about because you don't need to know capacitors that much. If you want to know about capacitors, he can show you in this video. I'm not going to show you this video. And then he's got a transformer right here.
Oscillating, pouring charge.
Because he's trying to make a taser. What does a taser do? A taser puts an arc across a 2-inch gap. Well, to do that, you have to have high voltage, like lightning. Lightning has voltage so high it's never been measured. And sure enough, there we go. There's his final schematic. What does he have? He's got a switch right here. He's got a ground right there. Capacitor, resistor. Right here is a relay. Plus 12 volts, that's B plus. He's got the coil right here, so that's the control part of the circuit. That's the power circuit right there. When this switch comes over here, that's a diode we're going to talk about probably tonight. Another capacitor, but the important thing is here's the transformer. And when you open up this switch, this transform, all this energy is going to come down here, turn into voltage, and search for a path to ground. Just make sure you're not that path to ground, right?
That's also what a Tesla coil does, correct?
Yeah, exactly. Sure. So
Wow. You can see how
it's a great video, but I'm not going to show it to you. But you make sure that's your homework. This is the first time I've ever done homework in adult school. How to make a taser. Yeah. He's also got another good video called Magic with Magnetism, which is a great video too, but it starts to get way too technical in the end, and I'm not going to show it to you. He starts talking about inductors and stuff like that, and it's like that doesn't do us any good. But it just shows you some interesting stuff about, you know, magnetism, whatever. All right, so let's go back. Hey, Rudy, I got a new document camera, so now people can actually see what I'm writing. Boom. Hey, when's your next hip surgery, dude? Oh, you already fell asleep. Okay, so transformer is used to change the voltage.
As soon as they reopen elective surgeries.
Dude, I had 17 elective surgeries in the last 6 months. You just need to get better insurance.
Well, my doctors told me that they've shut them down, so.
Yep, they are. The hospitals are full. What is it? San Antonio's full, so is Arrowhead.
No, mine's down in Downey.
Oh, okay. Well, yeah, the hospitals are full. There's still a lot of sick people.
Yeah, so they're saying no elective surgeries as of right now.
I know.
Well, I stay away from hospitals. They're filled with sick people. So, transformers.
Yeah.
We got 10 minutes, so let's see what we can do. All right, so what I showed you here was a small coil and a large coil with 1,000 times as many turns, whatever. That means it's going to put out 1,000 times as much voltage. This is the primary. That's where the energy is first.
My buddy Vadim's here. What's up, bro?
Hey, what's up, brother? How you doing?
Low voltage. And then this is the secondary, which is high voltage. This is called a step up transformer. Hey, where's Jerry Flores? And that's used to increase the voltage. Like in
Last time I talked to Jerry, he was really, really sick.
I hope he feels better. Or say a ballast for a fluorescent light. See, because what I was saying before, Gabe, about how the relay is also called a contactor. It's also called a controller. Well, the ballast in a fluorescent light bulb fixture is this. It kicks up the voltage super high so that when you turn the light on, the voltage is so high it's going to strike an arc all the way across the fluorescent bulb. That's what it does. That's how a fluorescent light works.
Jerry says he's recovering from high blood pressure and paranemia.
Paranemia? Yeah. Go watch your health, man. I mean, the thing is, when you're a teenager, you can do whatever the hell you want, but once you get older, you got to start paying attention.
Yeah.
Yep.
Hell yeah.
Okay, so that's a step up transformer. That means the voltage is going to go up, say from 12 volts to 12,000 volts, whatever. But that's not the only type of transformer. This is the type of transformer you're going to see in a power supply. It's going to have, say, 120 volts AC right here, and it's going to have an output of 20 volts AC. That is a step down transformer. And that means this is going to be the high voltage, and this is going to be the low voltage. So you're going to see this in cell phone chargers, power supplies for your laptop, power supplies for your scan tool, all that. You're going to see in a bunch of different places. You're not going to see these in cars that much because we don't need lower voltage usually. Okay, so a transformer is a member of the inductor family. What's induction? Induction is when they welcome you to the armed services. No, induction is something causes a change in something else without direct physical contact. I should write that down. Something, sorry. Yeah, now the resolution is so good, you can see how bad my writing is. Something causes change in something else without direct physical contact. Hell, if they reopen the schools, we'll probably be down there 24 hours. I'll just bring a cot. We'll do nothing but work on cars in 24 hours straight until May.
Hell yeah, I'm down.
Yeah, right. Probably take us that long to fix David Burke's brakes.
I hope not.
Yeah, I hope not. Okay, so what's an inductor? It's something that either creates a magnetic field when there's current flow, or, right, because this is going to create a magnetic field. And since it's AC, that magnetic field is going to be moving and it's going to be changing polarity. What happens when you move magnetic fields across a conductor? Creates voltage and current, right? So that's what a transformer does. It uses both of the principles of electromagnetism that we've been talking about. Uh-oh, forgot my iron core. And you saw the iron core, so you know what I'm talking about now. All right.
Thank you.
Okay, so we're going to use a transformer anytime we have a voltage we don't want, but we need a different voltage. You're going to see a lot of these. It's just a coil, folks. So you can test it just like we test any coil. Test it for continuity, test it for resistance. This is going to have way more resistance. Like, for instance, on an automotive coil, you're usually going to see, oh, shoot, now I remember. I wish I hadn't said that. 8 ohms here and 1.5 K ohms here. 1,500 ohms. Way more resistance. Why? Because it's going to be smaller wire, and it's also going to be a whole lot longer. You know, 4 things that determine the resistance of a wire: material, diameter, length, and temperature. I'm like struggling to remember. All right. So anyways, that's a transformer. Oh, incidentally, I need to point out that, you know, if you have 12 volts at, I don't know, 10 amps. Well, when this voltage goes up, what do you think happens to the amps?
Goes down.
It has to go down because the same amount of energy that comes in has to come out, right?
Yeah.
I mean, energy can't be lost or gained. It can only change forms. So if we got 12,000 volts, then we're probably going to end up with, I don't know, 0.01 amps. It's not a lot of amps. That's why it won't really kill you when you get shocked by, say, a spark plug wire. Also, we're going to lose some through heat, right? This thing is going to get warm.
But it does tingle very well.
It tingles pretty good though. Yeah, because your whole body is electrical. Now, what I was telling the kids, it's like your spinal cord is just a big conductor, and then all the nerves are going, you know, to all your different muscle groups. And, you know, when I got neuropathy, while we're on this topic, what they do is they put a sensor right here in your wrist, and then they put a voltage spike here. And what they do is they measure how long it takes to go there. They measure how long it takes to go a foot, and then they can tell, well, your nerves are shot, dude, because it's really, really slow. That's why if I touch something hot, I'm not going to know until it's freaking burnt.
That's not good.
Yeah, that's really bad, right? And that same thing's true with stepping on a nail, right? I'm not going to feel it until it's way up in my foot. I'll feel it then, though. That was a joke. So
Me too.
So the point I was trying to make was Gatorade's got electrolytes, right? What are the electrolytes, right? Electro, that's a hint.
Mm-hmm.
What they found was that athletes, when they were sweating, they were losing potassium, calcium, and magnesium, which are all electrically active chemicals. So what Gatorade was and why it works so well is because it replenished these electrolytes, which is to say things that made, I mean, what's the liquid in your battery called? Electrolyte. Right? See? That's what we want to do, folks. We want to understand everything.
If they could get rid of the sugar, it would be a perfect drink.
Dude, you got to drink the zeros, man. Be a hero and drink the zeros. Go to Stater Brothers. Quit going to your bogus stores.
59 cents.
I drink the zeros all the time. In fact, this was welcome advice. I was just telling someone yesterday, I calculated the amount of calories in a regular Gatorade. It's like 600. It's like you could have a piece of chocolate cake instead. I'd rather have a chocolate cake, right? So I'll drink one of these and have a chocolate cake, and I'll be in the same place you're at drinking full strength Gatorades. It's like, it's not worth it.
All right. Plus it gives you diabetes, man.
Yeah, it's got as much sugar as a Coke.
More like a batch of cookies.
Right?
Yeah.
You could have cupcakes instead. Everybody loves cupcakes. Yeah.
That's right.
Man, I can't wait. Chuck, can you imagine? They've opened up the freaking schools. We're going to have a freaking party. And when I say party, I mean wrenches flying like monkeys.
Cupcakes on our face, wrenches in our hands.
Grease just covered in grease. That'd be like the first 24 hours.
Yeah,
nobody ever wants to go home. Just drinking a bunch of coffee. No, I must fix more cars.
Yeah, that'll be great.
Yeah, I want it.
We'll just have to have a Starbucks truck parked right there out front of the classroom.
Yeah, like Beavis when he drank all that coffee. I must have coffee for my bone. Professional educator. Yeah, obviously, if you are unfit to teach in the state of California or work for our district. It is 7:30, folks. Let's take 15, and I will see you on time and ready to rock. Thanks, folks. At least this time I remember to, because the break is still in the video from last week. So we are talking about transformers, and we're talking about induction, which is to say something causes a change in something else without direct physical contact. So that means we're on the downhill slide because the electromagnetic devices are coils, solenoid valves, relays, transformers, motors, and generators. That's it. So this is a huge, huge chunk. This is like the foundation of modern technology. But the thing is, you have to understand electromagnetism or you're not going to understand it. But once you understand electromagnetism, and we don't have to understand why it works or how it works or anything like that, we just need to have a very basic understanding of it, enough to where we work, right? Because I don't need a PhD in dog psychology to teach my dog to sit. I don't. And I don't need to know how an engine works to start one up and drive a car. So the same level of understanding is adequate when we're talking about what we're trying to do, fixing cars, whatever. we're not trying to fix cars at an expert level. What we're trying to do is we're trying to have a foundational understanding. You know, if you want to learn to fix cars at a professional level, that's going to take 2 years full time of school. We don't have time like that. We got to rush. So, and you know, we're not trying to do that level of diagnostics. So here's what we want to do. We want to understand in a basic way how to test coils, because that's the foundation of all electromagnetic devices. Test coils and what they do. Transformers like that, I mean, you can test them for resistance. You can put voltage to them and see if it creates a magnetic field. You can put voltage here and see what comes out here. Just remember, this is high voltage. If you try to do that with a meter, you're probably going to get zapped. Plus, you have to disconnect this. You'll see it on the taser video. You have to disconnect this circuit in order to get the voltage to come out of this. But this thing, I mean, it's just, okay, I got a player's tip for you too. See that right there? This is the power supply for my scan tool. I figured this out. What you need to do is you need to get a Sharpie that writes in silver paint, and you need to take all of your stupid power supplies that you get confused with and they all get in a big jumble, and just write down what they go to. That way, when you see them in a big pile, or this is over here, the laptop's over here, and the scan tool's over there, that way you know what everything goes to, so you don't have to freaking sweat it so hard. It took me like 45 years to figure that trick out, but it's a good one. Okay, so, yeah, right. So I'm going to come in here, and I'm going to do a quick little jaunt through this, and I'm going to say, okay, well, how many volts should we expect coming out of this rascal? Well, let's see what we got.
110 AC.
120 probably. Let me see. Let's get this all in the same picture. And we come in here like that.
Your light is reflecting on the voltmeter.
Yeah, I know this has real bad problems with glare. I noticed that.
There you go.
And then this thing too. Okay, so what do we see? We see 118.2 volts AC. And you know, it was 119 a couple of maybe an hour ago. Okay, because it changes, but I don't think you can tell the difference. If you saw a light at 117 volts and a light at 121 volts, I'm not convinced you could tell the difference, because it's like 1%. It's less than 1%. So I don't think you could tell the difference. That's why we say it's 120 volts. See, it dipped down to 117. And it's proportional to the load on the system. Now, if the load on the system gets too bad, they just have a big dial at the power station that they crank up so that they keep the voltage at approximately the same place. But it doesn't really matter. It doesn't have to be, oh, I got 118 volts, you know, I got to replace all the wires in my house. That's what I'm trying to communicate. Okay, so then I'm going to plug in my, show you a little troubleshooting voyage here. I'm going to plug it in, and I've got this cable that goes to the power supply. Now, coming out of this cable, it's still going to be alternating current, because all this cable is doing is moving the 120 volts from here to somewhere else. So I'm going to come in here like this, and you see that it's the exact same voltage. That means the cord is good, right? I'm showing you systematic troubleshooting. So I'm going to come in here, stick this in the hole, and then I'm going to come out to the output. This is for the scan tool. Now, here's the thing.
That's with the DC.
Good, because this is to charge the battery in the scan tool, right? But the battery is not alternating current. The battery is direct current. Therefore, I need to change the meter to DC. Good, Rudy. So I stick the red lead on the inside, and I put the black lead on the outside. And sure enough,
I'm cheating my light. I'm using my battery booster as a light.
Right. 12.22 volts DC. So the power supply, the power supply is good. And you can do this with laptop power supply. In fact, it's interesting because the HP, that freaking charger for the freaking laptop puts out 20 volts. Now, I don't know what the batteries in the laptop are, but I'll bet you they're 15. If you got a 20 volt charger going into a 15 volt battery and you leave it plugged in, you're going to make that battery very warm. And batteries don't like to be warm. In fact, if you keep them warm long enough, they're going to say goodbye to you. So once you get the battery fully charged, disconnect the charger, because the flow of current creates heat. If you got 20 volts at the charger and 15 volts at the battery, you're going to be having current flow, and it's all wasted energy. Same thing is true, except I think you got 5 volts coming in on your cell phone charger. But that's how it works, and that's how you can test it. So, you know, you don't have to buy another one to see if it works. Now we understand, we've got a more sophisticated understanding. We can actually test things the right way. Now, I showed you where to get a Chinese version of this for like 18 bucks on Amazon, right? Just make sure it's auto ranging. It doesn't have 20 different choices here. It just has 1 volts DC and 1 volts AC. You don't have to get a 117. 117s are like 120 bucks and nobody's selling used ones. You can get meters at the pawn shop, but according to me, right, there you go. That's a Blue Point. It's a professional meter. This is the Chinese made Snap-on is Blue Point. But I got to tell you, folks, you know, you buy these from a pawn shop, you never know. It might be missing something. Something may not work unless you're going to test drive the whole freaking thing, which really I don't think you can. And if it's missing a fuse, that's like an extra 15 bucks. That's more than the meter costs from Amazon. So I would rather buy probably, I mean, and this is going to cost you 50, 60 bucks. I would rather buy 3 of the Chinese meters. I think you'd be better off. I don't think that the Blue Point is going to really be better. This is an older Blue Point, so the displays tend to be smaller. And I'm not convinced that it's going to give you worse service than one of the Chinese ones. Now, the leads, that matters. The leads will be professional. Remember, folks, if you're in a pawn shop and they're selling the meter without the leads, pass, because the leads are like 20 bucks. A professional set of leads, like the Flukes, like 20 bucks. And then all of a sudden, the meter you're buying isn't that good of a deal. You know what I've noticed is pawn shops are not cheap anymore.
I know.
Because, you know, why is because they've been in business this whole freaking pandemic and people have been losing stuff. So, and the fact that they can look up on eBay and see what everything is selling for, you got to be careful, because I've been in a couple of pawn shops where they were asking more than the stuff was new from Home Depot.
I know.
So don't get took, folks. Anyway, you don't need a Fluke. I mean, you know, like I said, I got Snap-on and I got Fluke, but that's only because now I don't have to work. So now I don't have to work. Now I don't have to wrench. So I've got all this ridiculous money. It's basically just an investment for me. So what I wanted to show you, which I thought was useful, remember this one, you got to make sure you get the DCM meter. It's easy to get ACM meters all day long. You got to get one that does DC. That's what's useful for us. In fact, if I had that 3-phase, oh shoot, doggone it. Why do I always put down heavy things? Okay. All right, 3-phase motor controller. I think Rudy's seen this once or twice. 3-phase motor controller. So I am going to.
I used to teach it.
Right. Okay, so there's a 3-phase motor controller. We go. Now, what I'm going to do here, Gabe, you watching? Gabe, you better be back. This is for you. All right, look, I'm going to turn my current to DC current. There we go. Turn it to DC current. Then I got to zero it because it's on 0 now. I'm going to put it on one leg, not both. I'm going to put it on one leg of the coil. Can you see that?
Mm-hmm.
Now I hit the switch. Come on. Oh, it's not DC. Sorry, put it to AC current.
Gotta be AC current.
Right. Thank you. Hit the 0, so it goes back to 0. Come on. There you go. Now we go. And you can see that it's pulling 0.2 amps, 0.2 of an amp, 200 milliamps. Right? Turn it off.
200 milliamps.
Turn it off. Turn it back on. Well, that glare is brutal, isn't it? Okay. That's how you do it. That's the usefulness of this device. And you can measure a whole lot of useful stuff with this, like charging system current, or you can do a starter draw, or maybe see how much a relay is drawing. All right. This goes here.
I got a test for that when we get back to school.
Okay, here's what I wanted to do.
Rowcliffe.
What?
I need to borrow that meter.
Okay, of course.
I need to find out what the current draw is on the starter for my flex.
Yeah.
Because it seems like it's lagging.
Check the connections. You know, Fords of that era are famous for bad battery cables connections where they hit the frame. So yeah, watch out for that, because what it'll do is, if that's the problem, it'll burn out your alternator, and then it'll burn out your starter motor, which neither of which is much fun. Okay, so here's what I'm going to do, because my good friend, whoever you are, I've got my power probe, and I've got my fan motor right there. Get this out of the way. Sorry, I'm kind of learning to move around the paraphernalia.
Don't forget to switch it back to DC.
Yeah, I just did. Thank you. All right, so I'm going to hook this up. See, we got 2 leads coming here. I want to see how much current this fan is drawing. Now, on DC, you can put the inductive ammeter on either side, because there's the same amount of current on either side. I'll put it here because it's more convenient. There we go. Come on. This is like the original 17 hand job. And then he said, let me do this the other way, like that. All right, so let me put this so it's closer to me. There we go. So I've currently got.
Tip it to the black or the red lead coming off the battery. That way we could actually see the screen.
Well, yeah. Good. Very nice. Well, I could go to the red or black lead, right? It don't matter.
Yeah. But at least this way we could see the screen.
Yeah, I appreciate that. Okay, so I'm going to stick 12 volts. Wow. That's a lot of current. Put this down. You're going to notice that the current goes way up and then it comes back down. That's because starting current is higher than running current. Just like starting to push a chair takes much more force than maintaining the movement.
Push.
Yeah. Okay, so let's see what we got here. Okay, you saw it went up to like 11, right? And then it comes back down to 7.5. See, Chuck, I told you it was a useful tool. It is. I mean, it really is. Yeah. There, I'm happy about that. Because what I wanted to do today is I wanted to focus on demonstrations. So I wanted to do stuff like that. This is why I dragged all this stuff from school to here. Now I want to show you something that I think you're really going to love. Yeah, what they said about reopening the schools is, Governor Newsom has reopened the state, and they offered us free vaccines at San Antonio. So, and I saw a bunch of trucks I saw a classroom that had been modified, which is freaking stupid. They got like 3-foot pieces of plastic, like germs can't climb the fence.
Right.
And I saw a bunch of trucks, you know, they're putting in plastic dividers and stuff like that. So nobody knows. So if anybody tells you they know, they don't. But since it's all political, like this freaking GameStop thing, since everything's political now, who knows?
Yeah.
Now, here's what I got. I believe Rudy's familiar with this little toy too. This is an old fan. I took the propeller off and I hooked up my battery operated. Yeah, it's nice. I hooked up my battery operated drill motor to the shaft on the motor. Well, all the motor is a magnet being pushed around by other magnets, electromagnets. So what I'm going to do is I'm going to get my oscilloscope. What can I get out of the way? I'm going to take my oscilloscope and turn it on. Put this thing under it so glare's not so bad. Waveform viewer, yes. AC pulse generators, yes. And I'm going to come in here. Remember, it's voltage over time. And you can see the sine wave starting to come from the induced voltage. I'm going to come in here. Whatever's highlighted is going to be what's changed. Yes, I want to change that. No, yes, I want to change that. I'm going to come down here to 0.07. I mean, sorry, 0.7. Come up here to 0.7. And yes, that's what I want. And you can see the sine wave, the induced voltage is coming from probably the computer power supply, I would imagine. So what I'm going to do here is, remember, electric motor works like this. It's got a magnet on the shaft, and we're going to have electromagnetic fields that are going to push that magnet around. So I'm going to take this connection here. I'm going to put this lead there and this lead here. So that's going to put it to the coils of the electromagnets, just like that. Oh, sorry, just like that. More chopsticks. Then you can see that when I have a rotating magnet, it starts to create the sine wave. Now, the time 50 milliseconds is too slow. It's too little of a time, and it's not catching full wavelengths. So what I'm going to do is I'm going to come here. Yes, that's what I want to change. I'm going to come up to 200 milliseconds, 1/5 of a second. And watch. Rotating magnets create alternating current. Now, if I turn it slow, you see that the voltage being created is very low in amplitude, and it's also very spread out because the frequency is very low. Frequency being how many times does this happen in a certain time period. Watch what happens as I change the speed. Now, I guess I could come in here like this. Hey, Chuck, you got a Vantage yet? Ordering one right now?
What was that again?
You got a Vantage yet?
Advantage?
Yeah, that's what this thing is. They're cheap.
No,
A couple $100 last time I looked. We'll see how much they are now.
Can I test coils in a car?
Yeah, absolutely. All day long.
Okay.
It's got the KV tester on the back. Yeah. As you can see, the faster the cutting action, the greater the voltage, and also the frequency changes. This is how your crankshaft position sensor, camshaft position sensor, vehicle speed sensor, input shaft speed sensor, output shaft speed sensor, and wheel speed sensors work. Rotating magnets creating voltage, and then like the ABS is just going to compare the signal coming out from all four wheels. And if I've got good signals coming out, the same signals coming out from 3 wheels, and then the last one has no signal at all, I know that wheel's locked up. Let's release the brakes going to that wheel because it's
I had
skidding.
to use my ABS the other day.
Maybe you should slow down. Quack.
I was getting on the 250. I was getting on the 215 from the 10, trying to get all the way over in the carpool.
That'll do it.
Freaking traffic stopped right out front of me.
All right, so what do you see?
It's a lot of voltage in a very short wavelength.
Right, that's because my scale is too low. So come over here to 1, come over here to -1. Because some of you are ready to start using oscilloscopes. And there you see that's induced voltage, that's the sine wave again. And come like this, come like that, and as you can see, this is an antenna, and when I go parallel to the light, it goes crazy. This is what people are worried about with 5G, is that you got a ton of these. 5G means 5 gigahertz. That's the frequency. And, you know, we've got all these electromagnetic fields rolling around us all the time. And am I really convinced that all of this electromagnetic radiation, which is what it is, I mean, radiation is just like sound radiates too. It's not like nuclear radiation, but am I convinced that all this electromagnetic radiation has no effect whatsoever on
They know it does.
the body?
They know it does.
Yeah.
They've already proven it.
The thing is, you know, if you ever look on these big power transmission towers, you know, they always have nurseries underneath them because they won't let people live near them. And if you built a house under one of those big transmission towers, the lights, you couldn't turn the lights off. Every time you touched something metal, it would shock you. So
electricity, free electricity.
Free electricity. I mean, what does Tesla say? Tesla says we don't need wires. But gee wizards, that's a whole bunch of stuff moving around, right? Hey Rudy, have you seen that movie, The Current Wars? Really should. You would love it. Yeah, you would love it.
Text me the name of it and I'll look it up on Voodoo, see if I find it.
The Current Wars. It's currently on cable. Okay, so
I'm sorry, I don't have cable yet.
Las Guerras Corrientes. Well, by the time you get cable, it probably won't be there. So
exactly, that's why I want to look it up on Voodoo. See if I could just buy it.
The Current Wars. So yeah, it's great. Well, you and I would love it, but everyone else would probably think we're just freaking nerds. Can you imagine thinking me and Rudy are nerds? What kind of world is this? Okay, so that's transformers. Now, here's what you pay your $80 for right here, folks. Full page drawing for sure. Full page drawing, and you're going to make the same drawing 4 times. There we go. Now, this does not have to be 10,000%, you know, straight, square, and parallel, but you just need to come in here and make 4 of these boxes as close to, as close to the same as you can. As you can see, my efforts are meager in that regard. Like this, like that. Rudy, did you have this house inspected?
Absolutely.
Oh, okay.
Everything looks good except there's some open grounds on some of the outlets, but they've all been rewired. And there's a offset on the sewer line at the connection to the clay pipe for the street. So none of that's really terrible.
Okay.
Compared to the last house that needed a complete rewire, a new roof, and the second kitchen in the 1-bedroom apartment was not permitted.
There we go.
Saying has not been tube over there.
Now, You make 4 of these things, which are actually field windings, in case you're wondering. Just a whole bunch of copper. Now, there's a million different motor designs, and the way a motor actually works is so complicated that I think you're not going to understand it if I explain the way it actually works. So I'll explain what's going on instead, because it has to do with this thing, and the current's going one way, the magnetic field's going another way, and the force is going another way. You can look up motors on Engineering Mindset, and it'll show you how it really works. But I think it'll just freaking confuse you. I like my explanation a lot better. And basically what it's doing is making it clearer and easier to understand for nuevecitos. So I got a bar magnet there. And this bar magnet is connected to a shaft. They call this the rotor or the armature, because they call it rotor because it rotates. And then this drawing is exactly the same, north and south. And that's connected to a shaft, which is connected to a pulley or a gear or some way of driving something. There you go. Doggone it.
That movie was $15 on Vudu.
What? It's free on
Yep.
cable. Okay, don't draw it like I just did. See, Rudy, I'm so unhappy. I just started thinking about the wrong things. Okay, so this is north and that's south. Doggone it. Of course I was on video. That helps. And north.
That's north, that's south.
Yeah, I was thinking of, getting my name on the Hollywood Walk of Fame, and I lost focus for a moment.
Don't lie, you were thinking about getting that red Corvette back on the road.
Yeah, seriously. Z06 is not meant to be a daily driver. That's how it's supposed to go. Basically, all that's happening is this bar magnet is spinning. Here, 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 and here. It's spinning. Now you say, why is it spinning? Well, I'll tell you why it's spinning. Because this is a north, and that's a south, and that's a south, and that's a north. That's a north, and that's a south, and that's a south, and that's a north. That's a north, and that's a south, and this is a south, and that's a north. That's a north, and that's a south, and that's a south, and that's a north. So if we were to follow the north fields, we would see it goes here, 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 here. So what's happening is, look, opposites attract, like charges repel. If I have a north and a north, they're going to push each other apart. If I have a south and a north, they're going to attract. So these two are going to push apart. These two are going to squeeze each other together. This south and this south are going to repel. This south and this north are going to attract. So what's this thing going to do? Since it's on bearings and it's got a shaft, it's going to spin. Now what we're going to do is we're going to take the two north fields and move them. And we can see, right, south to north attract, north to north repel, north to south attract, south to south repel. This thing's going to turn. And what we're going to do is we're going to move the magnetic fields around. And as we move the magnetic fields around, the rotor is going to turn. So this is called the stator sometimes because it stays in the same place, or the field windings, whatever. And this right here is the rotor or the armature. Rotor rotates, stator stays.
Same way an EV motor works.
Pardon?
Same way your Tesla motor works.
Mm-hmm. Yeah.
Rotates, and what was the second part?
The rotor rotates and the stator stays in the same place.
Thank you.
Thank you. Now, this is a simplified version, and of course, there's 85 different types of motors. But this is going to tell you all you need to know about electric motors, because I'm not trying to teach you how to rebuild motors. Right. Back when I went to freaking high school, we used to spend a week taking a starter motor apart and putting it back together. We don't have time for that now. We're not even close. I mean, cars are 3 times as complicated as they were back in '81. So as a result, we don't have time for stuff like that. We can't take apart starters and alternators and put them back together. I mean, I took an alternator apart, put it back together, but I don't think I ever learned how it worked. Keeps little hands busy though. See, one of the problems we have is that counselors now, they think that this is a hands-on class, like, oh yeah, just you keep idle fingers busy. Nah, no, we don't have time for that. I mean, we got hardcore stuff to, I mean, this is not, I mean, you take AP physics, you know, electromagnetism, you take those students and try to teach them this, and they'll be like, oh, I don't know what the hell. I know the formulas, but I don't know how the hell this works. Okay, so how can we make the motor turn stronger? Increase the strength of the magnetic fields, right? Increase the number of coils. All the stuff we've been talking about for the last, what, 2 or 3 class sessions? So
Or speed up the rotation.
well, yeah, but the motor has to be a certain speed. Oh, that's how we can speed up the rotation, is by increasing the magnetic field. Yeah, because it's going to increase the powers of repulsion and attraction. Yeah, that's why a stronger motor is going to be a bigger motor, because it's going to have more windings, right? And it's going to consume more power. If you looked at this 3-phase motor controller, you'd see that it's supposed to have number 8 wires. It's rated for what, 100 amps? I can't remember, but it's like, yeah, it's like 100 amps times 3, because it's a 3-phase motor. So that's like a 30, 50 horsepower motor controller. We can tell it's high power because of the size of the wires that feeds it. Yeah.
Okay. Yeah.
Now, here's the thing. How can we test the motor? Well, the motor's got coils, right? So now look, you can go to Engineering Mindset and watch their motors video, but you'd have to be pretty advanced to not freak out on how sophisticated it is. Plus, they start going into stuff that goes way over, it certainly goes way over anything we need to do. And in some ways, I wouldn't suggest it, because, you know, you might get demotivated. You know, so just watch what's there to, you know, to your satisfaction. And if you feel like bailing out, that's a good sign you should bail out, because the number one thing is we got to make sure we don't get demotivated, right? We don't get discouraged. And we don't need to know that much about motors, because after all, Rudy, if a motor's bad, what are we going to do?
Replace it.
Replace it. Yeah, we ain't going to fix these things.
Call Granger.
Yeah, call Granger. Yeah, quack. We ain't gonna fix motors. We ain't gonna fix solenoids. We ain't gonna fix relays. We ain't gonna fix coils. If they're bad, replace.
Honey, and a new lighter.
So solenoid valves, replace. Bad, replace. All we need to do is find out whether they're bad or not. Okay, solenoid valve, for instance, it's got a coil. We got to check the coil, make sure that the magnetic field is being created and that the valve is moving. Yeah, okay, then what? We make sure that the valve is working correctly, that it's not open when it's supposed to be closed or closed when it's supposed to be open. That's it. See, we got to quit thinking about this. Oh, well, this is some, you know, BMW part. I don't care who made it. As long as I know how it's supposed to operate, I know that a valve controls flow. Every valve controls flow. And every solenoid gets a plunger to move. Okay, that's all I need to know. I'm going to take my power probe, stick 12 volts to it, see if I get movement. Just like I said, like the relays, you know, the little bitty relays or the big old freaking honking 3-phase 480 motor controllers, it don't matter to me, because they're all relays and I know what a relay does and how to test it. Number one cause of failure on every electromagnetic device is always the coil. Always the coil. What does it do? How does it fail? Number one cause of failure. How does it fail? It opens. It opens because it gets too hot. The wires are too skinny and they go. Now, how does it get hot? From the flow of current or ambient temperature? Does the wire know? No, it could be a combination. Wire doesn't know. All it says is, I'm too hot, open. As soon as it opens, we have no current flow. No current flow, no magnetic field. That thing is dead and you ain't going to fix it. So why are you wasting time on it? Feel me?
Yeah.
Yeah, it saves a lot. It saves a lot of problems. And, you know, if I was to give you the textbook, they'd give you a 35-page explanation of how motors works. You don't need that. This is all you need to know. Now, are there brushes involved? Yeah, you'll see that on the motor video. But who cares if the brushes are bad? Rudy, what are we going to do?
Replace them. Replace
it, right? Yeah, we don't have to, like I said, we don't have to do an autopsy on it. If it's dead. This is the big change in mechanics And this is why, you go down a hole, you're going to see a whole lot of people that have rebuilt motors, rebuilt electric motors, well, even rebuilt engines. Chuck, we going to rebuild engines? No, we go down the store and buy one, and then we install it. Yeah, we'll install it, but in terms of building one, you can't make money doing that. You can't make money doing that. So we don't do it. And if someone says they want to rebuild your alternator, you need to run, because that's an old school, like vintage old school, way bad old school. No, we don't rebuild alternators. No. We vaya a la tienda y comprarlos. Yeah. It just doesn't make sense, because, hourly rate now is $120 an hour. It doesn't make sense to take apart alternators. No, if you're out in the jungle, okay, fine. But we're not out in the jungle. So that's electric motors, and that's about all I teach about electric motors, other than the fact that they've got coils, and you can just put, well, like I did. Okay, I'll show you. Okay, look. Here's an electric motor. In fact, it's an electric motor we know is good. So I'm going to come in here, and I'm going to test the coil to see if it's good. Okay, Chuck loves the continuity tester so much that I'm going to come in here, and I'm going to put it on continuity. See if Chuck's prophecy comes true. I go right there, and it's got 4 ohms resistance. I don't know if you can see that, but it's got 4 ohms resistance. And you can hear it. Yeah, see, 4, 3 ohms, whatever. Now that's going to change when you put current to it, but it's got 3 ohms resistance. Therefore, the coil of the motor is good. Therefore, if I put voltage to it, it's going to do what? It's going to spin. It has to. It has to. Down the road, right? This motor is not the problem. If there's a problem, the problem's going to be in the circuit. Now, am I going to verify this? Yeah, you know why? Because this could take 4 hours to get out from underneath the dash. So I'm going to verify that the circuit is getting voltage before I start pulling this thing out. And that's the big problem with these shops down here. They don't know how to do the basic troubleshooting I'm teaching you. So as a result, they're like, well, if the motor's not turning, it must be a bad motor. No.
They're charging you while they're trying to figure it out?
Yeah, they're charging you basically for their education.
Oh my gosh.
Yeah.
Good.
That's why we don't call it a profession. That's why we call it skilled labor. I mean, this is my industry, so when I talk crap about them, I'm not doing it from a position of ignorance. So that's an electric motor. Now, you probably thought electric motor was kind of complicated, and to tell you the truth, it probably is, but this is all you need to know about it. Like I said, I don't need a PhD in dog psychology to teach my dog to sit. I just need to know basic things that dogs are into. Kibble, crap. Okay. That makes sense?
Mm-hmm.
Now, you might have permanent magnets in here, but you're definitely going to have electromagnets in here. And that's what's going to make the difference in terms of power and speed. Now, Tesla invented the AC motor. Before that, everyone was like, yeah, AC is great, but we can't use it if you don't have a motor that works with it. Electric motors change the world, folks. If you in industry and stuff, what we're going to do, a water wheel in the river. So that's that. Now, let me ask you a question. I'm going to go like this with my bar magnet. North and south, little twirly thing right there. Ooh, perfect, perfect, perfect timing. And I got a coil right there. Passing a magnetic field across a conductor, and we saw this in the video. Passing a magnetic field across a conductor creates voltage or current. What determines how much voltage or current gets created? The proximity, the closeness of the parts.
And how fast you spin it.
Number of coil windings, how strong the magnetic field is, and the number of windings. Yeah, the speed of cutting action. I'm sorry. Yeah, you're right. Let me try this again. Proximity, number of coil windings, strength of the magnet, and how fast the spinning is. How fast the movement is, how fast the relative movement is technically. Okay, so if I was you, I would rewatch that part of the video because I think it's perfectly done It's exactly the way I would do it if I was doing it. It's in the alternator video, and it starts about 7:05 into the video, and it lasts about 4 or 5 minutes. Then it starts going into 3-phase, and if I was you, I would freaking ditch it at that point, unless my name was Gabe Alvarado, in which case I would start taking notes. Okay, so here I have the pickup coil right here. It's a pickup coil now. It's receiving,
Dave.
not what?
I said, go Dave.
Right? So here's the thing. This thing right here is the oscilloscope. And an oscilloscope displays voltage over time. Now, I know you guys are used to graphs where the vertical axis goes here and then the horizontal axis goes to the right. But in honor of moving the capital of Israel to Jerusalem, we are going to start on this side and go this way. That's kind of, yeah, that's kind of an intellectual joke. Obviously, I went to college too much. So this is how it displays on the Vantage, which is why I'm going to do it this way. And this is positive voltage here. That's 0 there. That's negative voltage there. And as this magnet spins, just like the video shows you, remember the name of the video is Engineering Mindset, and it's on alternators, and you started about the 7-minute mark. What's going to happen is, as the magnet goes by, it's going to start putting out a wave that looks like this. That's called the sine wave. Now, how tall is this going to be? Well, it depends on the strength of the magnet, the number of coils, blah, how close they are, blah, blah, blah. And also how fast this thing is spinning. The amplitude isn't the number one thing we're concerned about in this application. And this is how your crankshaft position sensor works, camshaft position sensor, vehicle speed sensor, input shaft speed sensor, output shaft speed sensor, those are on the transmission, and wheel speed sensor on your ABS. They all work the exact same way. Oh, it's also how your pickup coil works on your electronic ignition. Now, as I showed you, the question is, do you have a wavelength that looks like this? Or do you have a wavelength that looks like this? This one's rotating fast. This one is rotating slow. The difference is frequency. Now, frequency could mean how often do you take a bath? Frequency could mean how often do you feed your dogs? In this case, frequency means how often do we get a full cycle, which is from where the wavelength starts to where it starts to repeat. That's called a cycle. This is review from earlier, so anyways. What's a cycle? Spring, summer, fall, winter, spring, summer, fall, winter. Yeah. And we are concerned with cycles per second, EPS.
And your home is at 60.
Yep. I already demonstrated that. And that's frequency. And it's measured in hertz. HZ. Right there. And that's how the computer knows how fast something's spinning. But just this thing will generate current and voltage. That's how your alternator works. That's how your generator works. So the last page was an electric motor. And we can see that moving the magnetic fields causes the shaft to turn. Over here, we're rotating the magnet, and that's causing voltage and current to be created in the, see, this is turning mechanical energy into electrical energy. This is turning electrical energy into mechanical energy.
That's you accelerating in a Tesla, and the other one's you letting off the gas using
Uh-huh.
regenerative
Yeah.
braking.
Right. Okay. So I'm going to draw out this little electric motor so you know what this is. Looks like that. Put it on a little stand like that. Electric motor. Sorry, it's taking me a little time to get used to this camera and its parameters, but it does do the full page, which I kind of pleased. I just wish it was up.
There's the
bigger.
full page plus.
Yeah, and the resolution is 50 times better, so
It is.
that's good.
Oh
And
yeah,
that-
we can
yeah.
see how messed up your hands are.
Yeah, right. Yeah, I noticed that. I noticed that. Okay, so that's an electric motor. This right here is a generator. Now, when I'm using it as a speed sensor, I'm not using it as a generator. I'm not charging a battery or anything like that, but I am using the alternating current that gets created when you pass a magnetic field by a conductor. And it's going to create a wavelength like this, and I can check the speed of that to find out the speed of the engine. For instance, perfect. For instance, fuel pump. Fuel pump uses a fuel pump relay because it's a 30 amp circuit. It's got like a number 8 wire. It's big. We don't want big old wires going into the computer, but we want the computer to control the fuel pump. So the computer controls the fuel pump relay instead with a small current, micro milliamps, not micro milliamps. How does it work? As soon as you put the key in and turn it to on, ignition on, the computer is going to turn on the fuel pump for 2 seconds. That's going to pressurize the fuel system so that it gives you quick starting. Then, as you turn the key to start and crank the engine, the PCM is not going to turn the computer on. The PCM is not going to turn the fuel pump on until it senses rotation in the crankshaft. How does it know if there's rotation in the crankshaft? Crankshaft position sensor. Get it? So it's not going to leave the fuel pump on. If you turn the ignition on, it's not going to leave the fuel pump on for 45 minutes.
And if you ever run your car completely out of gas, you have to cycle the key 5 times before you try starting it.
That's interesting. Why? Because 2 seconds isn't going to be enough to build your fuel pressure? Yeah. Or, yeah, I would not run out of gas in a modern car. I would not run out of gas because it's so bad. So bad.
But it can happen. It can happen. It's happened to me.
Oh yeah, it's happened to me too. What does it do?
Well, it pulls all the sediment and crap off the bottom of the tank.
That's right. Yeah, that's not good.
So don't do that.
Okay.
I mean, it's got a sock and everything, but it's not bad. It's not good for the filter. Plus, remember the fuel pump is cooled by the fuel around it. So if there's less fuel around it, it's going to get hotter, and heat is a bad thing for motors.
I think that's what happened to me in Arizona.
Yep. Well, got to keep our fuel tanks full. You never know. GameStop could bring the whole freaking house of cards down. I only wish that was a joke, but it's kind of true.
It's true.
I must be living in a rock because I didn't hear about any of this.
All over.
Yeah.
I'm curious. I haven't heard about it.
GameStop stock has jumped almost 1,000% in the last 2 weeks.
Last I heard, they were going out of business. So that's I haven't heard about that.
We already talked about this, folks. We got to move on. We're out of time. Anyway, look it up.
Okay.
Look it up. So,
got it.
Folks, I got to tell you, that's all the electromagnetic devices there are. Coils, solenoid valves, relays, transformers, motors, and generators. That's it. How do you test an electromagnetic device? Test the coil, see if it's got continuity, see if it's got resistance, see if it's got an open circuit. Now, there's something here that I wanted to point out to you. because a lot of these electromagnetic devices, since there's such a spike when they open and close, they put certain things in them to keep that spike from destroying the coil, and it looks like this. Now, there is a great engineering mindset video on diodes, because that's what that is. This is a coil. This is the exact same coil with a diode on it. This one, if you put an ohm meter to it, is going to give you the same reading this way or this way, because ohms is not polarized.
Whichever direction you put it.
Whatever direction you put it. In fact, if I was you, just to make sure you're not getting bamboozled, if I was testing a coil, that's what I would do. I would swap the leads to make sure it gives me the same reading, to make sure that I understand what's going on in the circuit and I'm not going to get confused by some secret that I don't know. However, a diode is an electrical one-way valve, which means it's got high resistance in one direction and low resistance in the other. This is two resistances in parallel, which means you're going to get a different reading here and here. So watch out for that, because you're going to see these in solenoids and relays all the time. And if you're not careful, you're going to say, oh, it's got way too much resistance. No, watch out. Now, my question to you is, are there specs for all this stuff? Yeah, hopefully.
Yes.
In my experience, not so much. Not so much. You think there's specs for the resistance of the purge control valve solenoid? Well, there might be, but
there is. You just haven't found it yet.
I know what I'm going to do in terms of troubleshooting efficiency. I'm going to test, 15 different solenoids, and I'm not going to look up the specs on any of them. I'm going to test them because I know the number one fault on solenoids is an open. So I'm just going to test all these solenoids, make sure they got resistance. Chances are good, if I find a bad one, it's going to have OL, infinite resistance, which a coil can't have, because then you won't get any current flow. So what we need to talk about, and this is pretty much our exit from theory, and now we start going into systems again, which I'm sure will be a joy for everyone. There we go. This little rascal right here. It's black and it's got a silver stripe. Dog's like, oh, sounds like a skunk. And the symbol goes like this. It's got this little bar here and it got that little thing there. There we go. Looks like an arrow. This is a diode. And a diode, there you go, is an electrical one-way valve. What does a one-way valve do? It only allows flow in one direction. It's useful for a whole bunch of important things. So it's going to have high resistance in one direction and low resistance in the other. Now, folks, do not test these with an ohm meter because it's going to mislead you. You need to have a meter that has diode test on it, which is that thing right there. Man, look at the resolution on that camera. That right there, that's diode test. Now, while the question in a diode is high resistance in one direction and low resistance in the other, you can't test it with an ohm meter because an ohm meter doesn't have enough voltage to make it work properly. You need to use the diode tester because it kicks up the voltage way higher. Folks, you got to have a meter. I don't understand. I don't get. I don't know how you could do this without a meter. It's like I don't know how you're doing diagnostics without a scan tool. I talk to people all the time. They're like, "Oh, I think it's a fuel pump." I'm like, "What makes you think that?" And it's just a freaking guess. I'm like, you're guessing on something that's going to cost you $600. So I don't know how you do diagnostics on a modern car without a scan tool, and I don't really know how you do too much work on a car without a freaking meter. I don't. Now, why do we need to care about diodes? Because the diode's the thing in the alternator that's going to turn all that alternating current into direct current. We need to understand the diode because we're going to see diodes in a lot of places. Like, for instance, this is the door computer for the C5 Corvette. And what do you see here, here, and here? See those black things with the silver stripes?
Mhm.
Those are diodes. There's another diode here too, isn't there? Boy, this is great. Actually, I can see stuff that I can just use this anytime I need spectacles. Those are all resistors. That's a resistor. This thing right here is a capacitor. This thing right here is a, this thing right here is a transistor. That's an integrated circuit. Big old resistors. That's a transistor right there. See, it's a big black cube with 3 feet coming out. That's a power transistor. That's the microprocessor that runs the whole affair. That's another capacitor right there. Another capacitor right there. And 4 relays. Wow, that makes it easier to read. Look how small those part numbers are. Oh, they're big now. Huh? That thing melt?
You didn't
Now,
tell that.
I just need to point out, folks, that these things carry very little current. Those pins going to the door computer carry very little current. These carry lots of current. So these are control. These are power, right? These are the leads that go to the motors. These are the leads that go to the switches, for instance, because it's all going to be
To and from.
powered by relay, right? That's how you can use the key fob and it'll open the doors for you. Roll down the windows, whatever.
Or all of the above.
Rudy, we've been doing this crap a long time.
Way too long.
No, I don't think
But I
so.
love doing it.
Yeah, see, that's the thing. Once you get really good at it, it's like being good at golf. I mean, I hate playing golf because I suck so bad at it. But when I see the pure enjoyment that people that are good at it get, like Jim Knott, or the golf coach, the drafting teacher at Montclair, they love to play golf because they're so good at it. And now look what's happening to us. We've been doing this crap for so long. Golly, how many times do you think I've given this lesson? I mean, you've been there for 80 of them, right?
Probably
So
90 or 100.
So what happens, folks? Now we go into a situation and now we're not stressed. Now we're not panicked. We can go in relaxed and we can work way above our pay grade actually, because I mean, we may not have service information, or, Infinity may not give us this service information, but we know what a solenoid valve is. We know what it does and we
Or
know how to
Tesla.
test it. Yeah, whatever. Sure. Yeah. So we can go anywhere and work on anything because it's all the same. Or the bus, Proterra bus, it don't matter. Or Kenworth or Caterpillar. I found it very easy to go into the heavy duty program at Citrus and do well, because it's like, okay, so instead of having a solenoid valve that's this big, now it's this big. So
It's the same principle, pretty
it's
much.
the same principle.
Yeah.
And I took the freaking truck scan tool. We didn't have enough trucks to work on, so I just put it on the Corvette. I identified it as a truck of the same era, and it worked. And it's like every project they had to do that night, they could do on the Corvette, just because it's the same thing. Just like Michelle said, it's the same thing. A 350 truck, a 2000 350 truck is the same as a 2000 350 Corvette. I mean, as far as testing stuff goes. So it becomes really a delight and a treat. Did you catch that, Chuck? It really becomes a delight and a treat, as long as you don't ask me to actually fix anything, but talking about it, I'm there. If you want someone to talk about it, and Yeah, but anyways, it becomes much easier. And you know, I hope, Chuck Reyna, I hope I'm being helpful here. But you know, this is the kind of stuff that you can't learn on the job. This is the kind of stuff that you actually have to sit down and study. And trying to learn this in books is brutal. You
Yeah,
know,
it is.
it is. And you know, you look on YouTube, you're going to find 40 different videos about diodes, but there's only like 2 good ones.
Yeah, that's the thing.
Yeah. Now, the engineering mindset video on diodes is a great video, but if you try to watch the whole thing, you'd be like, what the hell is it? Silicon doping and blah, blah, blah.
It's just too extensive, or
It's just too extensive. Yeah. All I want to know is how to fix it. I don't really care how, to tell you the truth, I don't really need to know the nuts and bolts of how it works. I mean, that's nice and everything, but you know, I got a lot of stuff on my mind.
it's funny how much this is. It just reminds me of medical so many different ways. It's not even funny. It's the same thing pretty much, because it's, you got all the systems, you break them down, you know what I mean? It's very similar.
Yeah, it's the exact same thing, except you're working on people instead of cars.
Yep.
So it's an electrical one-way valve, which means it won't allow flow in one direction, which means it must be extraordinarily high resistance, and it'll allow flow in the other direction, which means it must be extraordinarily low resistance. That's what they mean by not allowing flow. It's just a matter of high resistance, low resistance. So that's indeed what you'll find if you're testing a diode. But you have to have enough voltage to pull it off. So you can't just use an ohm meter, even though we are testing resistance. So why do we care about diodes? Well, it doesn't look like we're going to have enough time, but here's what we got to do. I've got, well, do I try it? Yeah, let me just draw this so I'll know where to pick up next time. Okay, so here's an AC, whatever, who knows how much. And here's another AC coming this way, who knows how much. And the output is AC. I mean, this one's going to be smaller, but it's still AC, right? Higher voltage because it's got more windings. Well, so let's do this. Let us put a diode in one of the wires. Now, only the positive can get through and the negative cannot. Well, the wavelength that's going to give us is only going to give us the positive wavelengths. Not going to give us the negatives, going to give us the positives. See, the problem is what happened to the negative wavelengths? Well, I'll tell you what happened to it. They turned into heat. That's bad. This is called a half wave rectifier. Because to rectify means rectification means turning AC into DC. Why? So we can charge a battery. This is called a half wave rectifier because while it doesn't allow the negative wavelength to go through, all that power does is it turns into heat, a lot of heat. That's why we don't use half wave rectifiers, really, unless we had to. And you can see that there's a whole bunch of space right here where no energy is being transmitted. 10 minutes. I'm going to do it, Rudy. Here it comes. So I'm going to come off of this thing like this. I'm going to go this way, make yourself a diamond like that. I'm going to come around this way to here. I've got diodes here. I think this is how it goes. Diodes here. I got 4 diodes instead of 1. This way. And what this is going to do is, oh shoot, I think it's this one comes out positive. This one comes out negative. And now the wavelength we're going to get looks like this. Now it's going to give us all the positive wavelengths just like we had before. But now it's going to take these negative wavelengths and actually flip them over. So now it's going to look like this. See, what we've done is we've taken the AC signal here and we've rectified it into this. This is called full wave rectification. Because what have we done? We've taken all the negative wavelengths and we've flipped them over and made them positive. Now, this is pretty close to direct current. It's not direct current, but it's pretty close. It's all positive at least. Now, could you charge a battery like that? Well, I don't know, because when the voltage goes lower than the battery, what's going to happen? The current flow is going to back up. Yeah. Which is why if you look at the alternator, watch the alternator video, you're going to see that they're actually using three-phase. I think I discussed three-phase in this class. I'll have to check. If I didn't, I will next time. They're using three-phase so that the voltage never goes down to zero, and all you see is, you know, a little ripple on the top. Or what they were talking about using in the video that you can watch for homework is using a capacitor, and the capacitor will smooth this out so that we can charge a battery with it. Because remember, all we need to charge a battery is A, DC, and B, a voltage that's higher than battery voltage. Right? Pressure always goes from high to low. That's why fully charged batteries, 12.6 to 13.2 volts. Charging system voltage needs to be 13.8 to 15.2. See, it needs to be higher so that we get flow into the battery. That's it. I don't go for long technical explanations and I don't spend a lot of time on theory, but I got to tell you, I say I don't spend a lot of time on theory, but I'll tell you I teach more theory than anybody else that teaches this class, for sure. But that's because this is the only way I can understand it. I teach it the way it makes sense to me because I can't memorize stuff that good anymore. So I have to put it in simple terms that I can remember.
And it makes it a whole lot easier to learn.
Yeah, yeah, yeah. Because asking students to memorize all this theory, I mean, we all got problems. We all got a million things to do. I can't sit there and memorize that stuff. I guess I could, but I'm not motivated to. Well, if it's not going to help me, if it's not going to put money in my pocket or save me money or make my life better, why? There's so many things to do, so many things to learn. So watch the alternator video from Engineering Mindset. It's a great video. It's just there, it does get down in the weeds at some points and you're like, oh geez, dude. Tell you what, let's just watch a part of it. You got this, right? Let's just watch a part of it because I want to show you the part I want you to watch. We're here and it'll take just about as much time as we got. So let's go to how alternators work. Got it first time. Okay, so we're here where we left off last time. Let's go back a little bit, but not too much. There.
And now the opposite end of the magnet begins to get closer to the coil. And this pulls electrons in the opposite direction.
Hi, Roadcliff. How you doing?
Hey,
how are you?
And then decreases back to zero.
Doing better?
If we were to plot this current on a chart, we would get a sine wave with a current flowing in the positive and then the negative region. This setup gives us a single phase AC supply.
You watching, Dave?
Yep. But we have all this empty space between the coils, which seems a bit of a waste. So what can we do with all this space? Well, we can add more coils to create more phases and provide even more power. If we place another coil 120 degrees rotation from the first phase, this will give us a second phase. Why? Because the coil is at a different angle. so it will experience the change in intensity of the magnetic field at a different time.
So they're not synchronized.
The current is therefore going to flow forwards and backwards at a different time. That gives us another sine wave, which occurs at a different time. We still have empty space here, so we can add another set of coils at 120 degrees from the previous set to create a third phase.
How your alternator works.
If we use just a single phase, then for every rotation of the magnet, half the time the current is flowing forwards and half the time the current is flowing backwards. But with 3 phases, we always have a phase which is flowing forwards, and we always have a phase which is flowing backwards, which means we can utilize this to provide more power. Instead of having 3 separate coils and 6 wires, as the phases are always switching between forwards and backwards,
see this over
we can
here?
connect the ends of the coils together.
That's what it ends up looking
The
like.
current will
Now, folks, look. Can you see that as long as you have a single phase, you're going to go through 0 2 times every rotation? Well, look, if you do 3 phase, the voltage never reaches 0. As a result, you can use this to charge a battery. That's what 3 phase is all about. Look, if you have a single phase motor, Gabe, the voltage is going to go to 0 120 times per second. If you have a 3 phase motor, the voltage in the motor is never 0. As a result, you can deliver a ton more power, because power delivered is the area underneath this curve. Look at the area underneath these curves, right? You got all this empty space here and here outside the curve. But if you look in here, there's hardly any space outside the curve. That's the advantage of 3 phase. Because remember, DC means you got power all the time, all over. What we're trying to do with 3 phase is we're trying to get as close to that as we can with alternating current.
will then flow freely between each coil as it changes direction. Now we are producing 3-phase AC electricity, but all of our electrical circuits and components within the car use DC, or direct current. So we need a way to convert AC to DC, and for that we use a full bridge rectifier. This is essentially just 6 diodes connected in pairs and wired in parallel. Diodes only allow current to flow in one direction, and they block the current in the reverse direction. With a single phase supply, for every turn of the
That's
magnet,
a half wave.
current will only flow for half of the term. The other half will be completely blocked. If we connected each of the 3 phases separately to a diode, then the current will flow or be blocked at different times. Therefore, we can combine these phases into a block of diodes, and only the phase nearest its maximum will be allowed to pass through.
See, it starts to
This
get
gives us
complicated.
a slightly rippled DC
Check it out.
output.
That's called ripple, because all you're really going to see is the top of the wavelength. And if you have an oscilloscope, you can see this ripple. And if one of these diodes goes bad for any reason, you don't get this smooth ripple anymore. You get smooth, smooth, telling you that one of these diodes is bad. You can find this ripple on an oscilloscope.
To smooth this ripple out, we can connect a capacitor, which will basically absorb electrons and then eject electrons automatically to maintain a constant output. This gives us a constant smooth DC supply. By the way, we have covered diodes,
and you will not understand, at least I didn't,
capacitors and power inverters in great detail previously. Do check those videos out. Links can be found in the video description down below. Okay, so now we have a DC output. But if the magnet is connected to the engine and the car speeds up, then the magnet will spin faster, and that will increase the output voltage and current. We don't want that, because it will kill all of our electronic components within the car.
overcharging.
So we need a way of regulating the voltage. If you remember, we saw that by using an electromagnet, we can increase or decrease the electromagnetic field strength by varying the voltage. And by varying the strength of the magnet, we can vary the voltage and current generated in the coil. That's why the alternator uses an electromagnet, so that it can control the output. The car battery powers the electromagnet, although most modern alternators will use a diode trio, which converts the alternating current of the alternator into direct current and powers the electromagnet via a voltage regulator once the alternator is generating electricity. On the power supply of the electromagnet within the regulator, we find a component known as a transistor.
See, now it's getting complicated. Now it's probably losing you. And okay, Chuck's probably ready for this. Maybe Rudy's ready for this. But unless you have a pretty hardcore understanding of vehicles and electronics, this is where it gets freaking complicated. And I don't think it's helpful. All you need to know is that the voltage is regulated by regulating the strength of this magnetic field. The output of the alternator is regulated by regulating the strength of this magnetic field. And it's done by the voltage regulator anyway. So if the voltage regulator goes bad, what are we going to do, Rudy?
Replace it.
We're going to replace it. We're going to replace the whole unit because it's integral. It's one unit, the alternator regulator. So, you know, if the alternator's output is good, you know, if I start the car and the voltage goes up a couple of volts, charging system works. Now, Rudy's brought up an important point, and I know we're going over, but this will take a couple of moments. Rudy's brought up an important point, especially on the Fords of the era from, I don't know, mid 80s to mid 2000s. There was something wrong with their battery cables and their battery connectors. And what happened was you ended up getting high resistance in the ground cable or the battery cables in general. And what happened was, as a result, now the alternator thinks that the battery's not charged, so it keeps pumping overtime. So you end up burning up the alternator. Even though the battery's fully charged, the alternator doesn't know that because you got connections problems. And also the starter starts to run slow, so it starts beating the hell out of the starter. So typically what happens on these cars, when the cables go bad, people replace the starter motor, they replace the alternator, and they replace the battery, and it still doesn't fix it. It's because it's the cables. So that's why we want to do the voltage drop test. That's why we want to know what to look for. And I think teaching you that, spending 5 minutes teaching you that is way better spent than you learning about transistors in the sensor controller in the freaking integral voltage regulator that you're never going to see anyway. Yeah.
Makes sense.
All right, folks, it is 9:03. Sure had a great night. You know, this is the way to cap off a day, because it's a 13-hour day. It's a rough day, man. Yeah. But this is certainly the way to cap it off, because I'm not dealing with discipline issues and I don't have to babysit, and it's wonderful to have conversation with such lovely people.
Yes, and we love your class.
Thursday Gigante, right? No, I'll see you in February. I'll see you next month.
Yep.
Can you believe how fast that went?
Mm-hmm.
No, not at all.
It's Valentine's Day.
By next class, we'll be a new homeowner.
Cool. So we'll hold it. So I'll bring all my stuff and we can set up live from Rudy's house.
I don't know if I'll have internet yet.
I'll bring my own. I'll bring the satellite truck.
There you go.
It'll be like MTV. Quack.
Go.
You're making tacos.
Yeah, making tacos and cupcakes.
There you go.
Oh yeah.
All righty. Thank you.
Appreciate it, folks. Thanks so much.
Okay.
I'll see you next month. Yeah.
Yep.
Thank you.
All right.
Tell your wife to get better.
Good night.
Bye, Rudy. Bye, everybody.
Bye, guys.
Bye.
Good night.